Cool. Okay. So yeah, thank you all for having me. It is really nice to be able to give a talk to all of you. So the title of my talk today is Partial Observables and Kinds of Redundancy. So I'm going to be talking about this question of what makes something redundant to a theory. And the reason this question is important for philosophy of science and philosophy of physics is that we want our best theories, it seems to be absent of any kind of redundancy. And why is this? Well, one reason one might give is a kind of Occam's razor kind of reasoning that if we have two theories that make all the same empirical predictions, and one is simpler than the other in that it has fewer redundancies, then we ought to accept that simpler theory. And another kind of reasoning that one might give that's related to that is that we want our theories to tell us what really exists in the world. And so if we have some quantity in our theory that we don't think corresponds to anything real in the world, then we think that we ought to get rid of those quantities from our theories. So there have been several strands of literature that have aimed to answer this question of what makes something redundant to a theory. And in this talk, I'm just going to look at a couple of these kinds of characterizations, but I'm particularly going to be looking at the arguments that one can give against these characterizations as picking out redundant features of our theories. And the reason for doing so is I think there's less clarity in the literature on how to spell out these kinds of arguments. And what I'm going to try and do is try and relate the arguments that one can give against redundancy in these two different contexts in order to shed light on what one might see as the core problem with these arguments for redundancy. So just an overview of how this talk is going to go. I'm going to start by describing these two kinds of characterizations of redundancy. The first is the notion of a gauge variable, in particular as it comes out of what's known as the constrained Hamiltonian formalism of a theory. And the second context is the notion of excess structure in a theory, which comes out of the literature on how to characterize and compare the structure of theories. And I'm going to break this notion of excess structure down into two ways in which one might say that some theory has excess structure. And then I'm going to turn to the arguments that one might give against these characterizations as picking out what's redundant to a theory. So in the context of the notion of a gauge variable, I'm going to look at an argument by Clara Bradley that we should not get rid of gauge variables from our theories because they play a role as what he calls partial observables. And what these are will become clear later. And then in the context of excess structure, and in particular, one of the two kinds of excess structure that I point to earlier, I'm going to look at some arguments for the role that isomorphic models play in a theory. And I'll demonstrate why looking at these arguments has relevance for this question of whether this kind of excess structure picks out redundancy in a theory. And then finally, I'm going to try and relate these arguments against redundancy by drawing on a distinction that I'm going to make between two kinds of physical significance that one might say that some structure in a theory has, where I'm going to argue that some structure can be redundant in the sense of not having one of these kinds of physical significance without being redundant in the sense of not having the other kind of physical significance. And I'm going to argue that the most plausible interpretation of these arguments against redundancy is precisely as picking out this distinction and arguing that the problem with the arguments for redundancy is that they conflate these two notions. Okay, so first, this notion of a gauge variable as it comes out of what's known as the constrained Hamiltonian formalism. So first, I'm just going to briefly go over what this constrained Hamiltonian formalism is. The details of this are not going to be super important for my talk. The main reason for just spelling it out is just to motivate this idea of what a gauge variable is. So just to spell out what the constrained Hamiltonian formalism is, it starts in what's known as phase space. So phase space consists of, the points of phase space consist of all the position and momenta of the particles in the system, where these momenta are these generalized notion of momenta given by the derivative of the Lagrangian with respect to the velocities. And in addition, one has a set of constraints, which one calls primary constraints, which link these position and momenta of the particles in the system, and we set this constraint equation equal to 0. And now one can define what's called the total Hamiltonian, which is just a sum of the usual Hamiltonian and a linear combination of the constraints, where these coefficients, these UMs, have some arbitrariness in them. And the idea is that when the constraints hold, when these primary constraints hold, so when the constraints equal 0, then this total Hamiltonian is just dynamically equivalent to the usual Hamiltonian. And then in addition, the equations of motion for this formalism for some dynamical variable g, say, is just given by the Poisson bracket, which is just some binary operation between that variable and this total Hamiltonian. And now one can see that the primary constraints are some relationship linking these q's and these p's. And by consistency, it must be the case that the time derivative of those constraints is also equal to 0. And so we can use the equations of motion on these constraints to give rise to some new relations between the q's and the p's when this reduces to something independent of these coefficients u. And we call these kind of constraints that come out of applying the equations of motion to the constraints the secondary constraints. And we can repeat this process by thinking of the time derivative of the secondary constraints equal to 0, and one can get more constraints of this kind. And just a definitional thing, we say that a constraint is first class if the Poisson bracket with all the constraints is 0 when the constraints are satisfied. Now, the important part of this formalism is that there's some arbitrariness in how one sets these coefficients in the total Hamiltonian, even when one takes into account all of the constraints. And this means that the evolution of a system can be underdetermined, in that there might be different possible values for a variable at later times given its value at some initial time, because the evolution of some variable depends upon its relation to the total Hamiltonian, which has this arbitrariness by fixing these coefficients. So depending on the choice one has for these u's, one might get a different value for these variables. And those variables which are underdetermined in this way, we call the gauge variables, and those which are not, we call the observables. And formally, one can show that the observables are just those variables which have 0 Poisson bracket with all the first class constraints. So I won't go through why this is the case here, but the idea is that if one considers the evolution of the variables that have 0 Poisson bracket with all the first class constraints, then this will lead to a value that's fixed for all times, because it doesn't have this arbitrariness given by any kind of dependency on these coefficients u. Okay, so given this distinction between the gauge variables and the observables, one might be led into the following kind of argument. One might argue as follows. One might say, well, first, given a complete specification of the initial conditions and the constraints for a system, there is a single possible physical evolution of a system. So this essentially is an assumption of determinism. It says that if you know everything you can about the initial state of some system, then there's only one way that it can be in the future. Now, second premise, if the equations of motion do not lead to a unique evolution of the system, then the source of underdetermination are the gauge variables. And so this is just what we said in the slide before, that the reason one doesn't get a unique evolution is because there are some variables whose value depends upon how one sets these arbitrary coefficients in the total Hamiltonian. And so 3, since these different evolutions are physically equivalent by the first assumption, the gauge variables are not physically significant and therefore are redundant to the theory. And finally, since they are redundant to the theory, they should be removed from the theory in order to remove the underdetermination present. So I'm going to come back to these last two steps of this argument, but the intuition that's going on here is that it's the gauge variables that are causing this problem. And so one doesn't think that they shouldn't correspond to anything physical in the world. There's no way to tell which way this gauge variable should be set. And so they don't play any role, it seems, in the physical content of the theory. And so we should just get rid of them from our theory altogether. So there have been several people that have put forward an argument just like this. So I'm just going to give a quote from Gordon Bellot. He says in a 2003 paper, "Because the points of such orbits are dynamically indifferent." So the orbits here is just a technical way of talking about those points whose difference just lies in the value of the gauge variables. Because they're dynamically indifferent, the gauge variables are dynamically irrelevant. Any way of setting their value leads to the same evolution. This suggests in turn that it may be possible to drop the gauge variables from our theory altogether. And he goes on to argue that we can remove the gauge variables by moving to what's known as a reduced phase space, which technically is just take phase space and you quotient it by these gauge orbits. But the important thing is that on this reduced phase space, only the observables are functions on this space. And so there's a sense in which one's got rid of the gauge variables because one can't even define them as functions on this reduced phase space. Okay, so this is the argument that one might give for gauge variables being redundant and therefore that we should get rid of them by moving to this reduced phase space. So now I'm going to turn to this other context, this context of characterizing what is excess structure in our theory. And I'm going to say there are two ways in which one might say a theory has a kind of excess structure. The first is that a theory has non-isomorphic models that correspond to dynamically equivalent situations. So non-isomorphic just means that they're different according to the theory. They don't have the same structure, and so they can't be interpreted as representing the same situation. So one common example that's used to demonstrate this kind of excess structure is take the theory of Newtonian gravitation set in a space-time that has a fixed notion of absolute rest. Then if one takes a model of this theory and applies a velocity boost, then one gets a new model where everything is moving at a different velocity relative to the absolute state of rest. But, and so because there's a different velocity, this model is non-isomorphic from the first, but one cannot tell which situation one is in because there's no way to tell whether everything is stationary or moving in a straight line. And so one thinks that this absolute state of rest is some surplus structure that we ought to remove from a theory. So this is the most common way in which this term excess structure has been used. But I think there's another way that it's been used in the literature that one should also consider. And this is when a theory has distinct but isomorphic models that represent the same situation equally well. So the idea is that a theory might have models where there's a sense in which they're the same, there's a notion of their structure being equivalent, but there's also a sense in which they're different, where what makes them different is not the structure of the theory, but rather some structure one uses to describe the models of the theory. Now, one might ask, well, what kind of excess structure is this second kind supposed to be if these models don't differ over the structure of the theory? And the answer is that it seems there's a kind of excess choice of which model one uses to represent a single state of affairs, or one might say a kind of representational redundancy in virtue of there being multiple ways to represent a single situation. And so this might lead one to argue that we ought not have distinct models of the situation at all, but we ought to move to a theory where these models are just identical. There's just one single identical model that represents this situation. So just to spell this out using an example, I'm going to take an example from a paper by Samuel Fletcher, although he's adapted this example from an earlier paper by Gordon Bellod. And the idea of this example is that one considers Minkowski space-time with a single particle in it. And one's going to take two models of this theory. In one model, the particle swerves to the left direction, and in the other model, it swerves to the right. Now, these models are isomorphic in this theory because one is just a rotation of the other, or might say a reflection, but one's a rotation of the other, and a rotation is a symmetry of this theory. And so it seems one could choose either of these models to represent a swerving particle. And we think they would be equally good as each other because a swerving particle wouldn't be able to tell which direction that they're swerving in. And so whether we say that they're going to the left or to the right doesn't seem to matter observationally. So just to demonstrate what it would have to be the case for these models to not be isomorphic in the theory, that is, if they, in addition to the structure in these models, one had some structure that distinguished left and right. For example, one had a privileged direction in this theory, which one could view as just adding an arrow in both of these models that points in the same direction, just like this. Then only one of these models would correctly represent swerve to the left, because these are now non-isomorphic in this theory. But now this kind of situation would lead to a problem of excess structure of the first kind, since these models would correspond to distinct situations in the theory, but they're dynamically equivalent because one couldn't tell one couldn't pick out observationally what this privileged direction is. So let's move back to the case where these models are isomorphic. In the case where they're isomorphic, it seems both models represent a single situation, namely the swerving particle, equally well. And so there's a kind of excess choice of which model one uses to represent a swerving particle. So one might think that one should move to a theory without such excess. And if one looks at these models, one sees that the difference is the direction in which they swerve. What's common is just how much they swerve. And so one might think, let's move to a theory where the models of that theory are just models of the amount that it swerves, or one might say the absolute distance of the swerving particle away from some origin point, because then these left and right models would just correspond to a single identical model. And for the philosophers of physics in the audience, one might see this kind of argument as similar to that, which argues that the whole argument demonstrates that general relativity has some excess structure because it gives rise to models that are isomorphic, generated by this whole diffeomorphism, but they also differ over the value of the metric at points in space-time, and so one should find a way to remove this excess by equivocating between these models in some way. In other words, this kind of argument says it's not enough to just interpret these as equivalent. It says that generativity has some kind of excess that we should get rid of. So just to recap what I've said so far, we saw that in the context of gauge variables, one could generate this argument, which led to the conclusion that these gauge variables are redundant because they lead to physically equivalent trajectories, and therefore should be removed by moving to this reduced phase space. And similarly, the argument in the context of excess structure depended on whether we referred to this case where models are non-isomorphic or isomorphic. But in both cases, we led to this conclusion that whatever distinguishes the models is redundant, whether it's theoretical structure or descriptional structure, and therefore it should be removed from the theory. So now I'm going to turn to the arguments that one might give against these characterizations of redundancy as picking out, in fact, what is redundant to a theory. So first, in the context of gauge variables, I'm going to look at this argument that Carlo Rovelli gives for them not being redundant. And he's particularly looking at this feature of theories that it seems that despite gauge variables not being predictable in our theory, it still seems that they play an ineliminable role in our physical theories. And he wants to provide an argument for why this is the case that isn't just about it being a practical thing. It's not just that they're useful to be in our theory for some practical reason, but that there's actually a physical reason why gauge variables are so important to our theory. And the way he argues this is he says that gauge variables should not be removed from a theory because they may play a physical role when systems couple with each other. And the variables that play this role he calls the partial observables. So coupling is just when you have two different systems and you think about them interacting in some way. So to motivate this claim, I'm going to look at one of the examples that he gives. And this is an example of two systems of spaceships. So the idea is that we're going to take two systems of spaceships that each have two spaceships within them. So I'm going to look at this case of two spaceships per system. And so Rovelli characterizes the Lagrangian of each of these individual systems when they're disjoint from each other as given by the following. So we have the X systems and the Y system. And the Lagrangian is just given by a relation between the difference in the velocity of the two spaceships in this system. So one can see this as just characterizing the kinetic energy of the system, where the velocity we're considering is the relative velocity of the two spaceships in the system. And now if one runs through the constrained Hamiltonian formalism, one finds that the observables of these individual systems is given by the difference in the position of the two spaceships in the system, whereas the gauge variables of these systems are the individual positions. And just to see why it would come out like this, if one thinks about the symmetries of these Lagrangians, so what we can do to preserve the Lagrangian, if we add a constant to the gauge variable, so if we add a constant to all the positions, then this means the position seems to change, but it preserves the Lagrangian, and it preserves this relative position. And so it's the relative positions that are preserved by adding some constant to the individual positions. And so these are the things that are the observables. But now Rovelli says, let's consider interacting these two spaceship systems together so that now the joint Lagrangian of this total combined system is given by the sum of the Lagrangians of the individual systems, but also another term given by some relation between the difference in velocity between one of the spaceships in one of the system and one of the spaceships in the other system. And now one finds that the observables of this combined system are given by the observables of the individual systems, but also another observable, which is given by the difference in position between one of the spaceships in one of the system and one of the spaceships in the other system. So one has more observables than just the sum of the individual systems. And so what Rovelli draws from this is that if one had run through the argument I gave earlier that we should get rid of the gauge variables and just formulate everything in terms of the observables, then this would say we should formulate the individual Lagrangians in terms of these Cx and Cy. But then if one did so, then one wouldn't be able to describe this coupled system, this joint Lagrangian, without introducing a new variable, namely one that depends upon the gauge variables of both systems. And so what he says is that it seems that we shouldn't get rid of gauge variables from our theories because they may play a role when we want to couple systems together. So I think this example is illuminating into this idea that partial observables play some kind of coupling role, but I think it still leaves some unanswered questions for this program. So one question that I have for Rovelli is, what role does the spaceship example play in showing that gauge variables in general should not be removed from a theory? What it seems to demonstrate is that we ought to be careful about considering a subsystem versus a whole system because the symmetries of one might not be the same as the symmetries of the other. And correspondingly, the observables might not be the same. But this doesn't seem to say that if you give me any theory with a specified domain of application, that we shouldn't get rid of the gauge variables from this general theory. And another question is, what is the physical significance of these partial observables supposed to be in contrast to the complete observables? So the complete observables are the observables that I considered earlier, the ones that aren't gauge variables. And Rovelli says that in a sense, these partial observables are the quantities with the most direct physical interpretation in the theory, despite the fact that they are not predictable. But how do these two things square up? How can it be that they're not predictable in the theory while also having this most direct physical interpretation? And Rovelli says things like the partial observables are measurable, even though they're not predictable. But then we need some account of what it is to be measurable in a way that understands what this physical interpretation is. So I'm going to come back to these questions later. I'm now going to turn to this context of characterizing excess structure in a theory, and in particular, the kind of excess structure that came from isomorphic models. And I'm going to think about the arguments one might give for why this doesn't correspond to a case of redundancy. So we said before that isomorphic models seem to be equivalent for representational purposes. That is, it seems that they just represent the same situation equally well. But some have argued that this is wrong. There are cases where isomorphic models are importantly distinct from each other, in the sense that they have importantly different representational uses. So for example, Gordon Bellot argues that isomorphic models can, what he says, generate new possibilities, and particularly modal kind of possibilities, while a paper by Brian Roberts argues that the differences between isomorphic models can have a kind of representational significance. And I'm going to look at this, how one spells this out in the next slide. But the idea is that these kinds of arguments suggest that isomorphic models don't necessarily contain redundancy, because there's some important representational difference between them, and therefore that we ought not reduce them to just one single model. So just to look at how one might spell out Brian Roberts' argument. So Brian Roberts uses the following example. He says, take the model of the half Minkowski plane. So take the half Minkowski plane, then consider a new model that you generate by just shifting up the half plane by some amount in time. Now, this shifted model is isomorphic to the half plane, since time translation is just a symmetry of the half plane. And we're considering shifting up in time by some amount. But there's also a sense in which the second model is a subset of the first model, since it's represented as starting at a later time. And so formally, it seems there's some non-surjective inclusion map from it to the half plane. So there's a sense in which it is also just a subset of the half plane. And so Brian argues as follows. He says, a subset of a space-time is physically distinct from a full space-time. That is, a subset is a physically different situation than having the full space-time. Therefore, one cannot use one model to represent a physical space-time, and simultaneously, so in the same interpretation of the theory, use its subset to represent that same space-time. But as I said, these models are isomorphic, one's just a translation of the other. Therefore, he says, isomorphic models cannot always represent the same situation in the same interpretation. So this seems to suggest that although these models are isomorphic, there's an important distinction between them that means they shouldn't be used to represent the same situation at the same time. So one way one might respond to Roberts is as follows. One might say, well, on what basis can one say that a subset of a space-time is physically distinct from a full space-time when these models are in fact isomorphic, and so they preserve all the structure of the theory? So on what basis are you saying that these correspond to physically distinct situations? And in particular, it seems that in order to distinguish the half plane and its subset, or even to say that one of these models is a subset of the other one must have some way of fixing the time attached to events across the models. And in effect, what this means is having kind of fixed label to the time axis so that one can say that the translator model starts at a later time and is therefore a subset. So for example, if the axis of the half plane was fixed like this, then the translated model with the same fixed axis would look like this. So it starts at the time 2 compared to the original one, which starts at the time 0. And this is what would allow one to say that the second model is a subset of the first. But the theory doesn't fix this structure precisely because time translation is a symmetry of the theory. And so any such choice of time axis is isomorphic to any other choice. And so it seems that one has no way of saying within the structure of the theory that the second model starts at a later time. It's only at this kind of descriptional level in the way that one talks about these models. So how could one distinguish these? Well, one way one might do this is by considering how one could interpret these models, and in particular, what structure one could use to represent that something physically distinguishes the subset case. So for example, one way one could do this is to choose some structure to represent a physical clock so that one can now talk about the time of events relative to that clock. Then if one moves all events to a later time according to this fixed clock, then this seems to meaningfully give rise to a distinct situation. It now corresponds to a case where things are later according to this clock. But it seems it's only by fixing this clock structure and its interpretation that one can distinguish a space-time from its subset. So one might respond by saying that, well, haven't you, by fixing this structure, merely just added structure to the theory now and considering a new theory where these two models are now non-isomorphic? But I think that this kind of argument is confusing what one takes to be part of the structure of the theory and what one takes to be representational choices that one can make given the structure of the theory. That is, just because the theory doesn't fix the time attached to events, that doesn't mean that one can't represent a clock within this theory, where this clock assigns a time to events. Now, because the theory doesn't have this fixed structure, there are different choices that one can make that would be equally good. But once one picks one of these choices and fixes its interpretation, then one can talk about situations relative to that fixing. And in fact, it seems that if we had added structure to the theory to make these models non-isomorphic, then we would seemingly have excess structure of the other kind, since this would be like adding a fixed label to the time axis, which is like saying that this theory now has an absolute time kind of notion. And then we would seem to be in a case where we have non-isomorphic models that can't be distinguished. So I think it's important that although we might want to treat these as isomorphic models, this doesn't mean that we can't use some structure within this theory to distinguish them. And so I think that one can therefore maintain that the half plane and its subset can represent the same situation in the same interpretation of the theory, while agreeing that they can be used to represent distinct situations. So this is like disagreeing with Roberts that they can't represent the same situation at the same time, but that they also can be used to represent distinct situations when one fixes some structure in order to physically distinguish them. And I think one can give a similar kind of argument in the swerving case that we considered earlier. So in this case, one can say that if one chooses some structure to represent a particle that is to the left of the swerving particle, then once one fixes this particle that's to the left of it, then one can say that in the first model, the swerve is to the left, and in the second, it's to the right, relative to this fixed particle. Because in one case, it's moving towards this particle, in the other case, it's moving away from it. And so it seems that if one wants to be able to represent these as distinct situations, it seems important that one should have models of the theory that can be distinguished by fixing this standard of what one takes to be left and right. And so having choices that gives rise to these isomorphic models seems important to be able to represent these situations as distinct, even though these models can represent the same situation equally well. And I think this gives a more general argument against that one that I gave earlier, that one should get rid of these choices so that there is only one identical model instead of multiple models. So for example, in this swerving case, we said that one way to get rid of these representational choices is by moving to a theory of the absolute distance away from some origin point. But if one did so, if one moved to this theory, then one wouldn't be able to represent these distinct choices of left and right, because one has, in effect, got rid of any way to specify the direction that a particle swerves. And so it seems if one wants to be able to represent these as distinct situations, one shouldn't move to this case where there's just an identical, where these models are just identical to one another. And in fact, Samuel Fletcher, who gave this example, also gave this kind of argument. And so here's a quote by Fletcher. He says, "Users of relativity theory, I claim, would intend for the theory to endorse that the particle could have swerved at the same acceleration in another direction when even at another time. Proposals to identify isomorphic but non-identical models in various ways, which are often motivated by a desire for representational uniqueness, perhaps for metaphysical ends, also must face the awkward problem of how to represent these distinct states of affairs with a single model." Now, Fletcher goes on to argue for one way to represent these as distinct, which is slightly different to my argument, but I take it to be making essentially the same point. And his argument is that there's more than one map that relates isomorphic models than just the isomorphism. So he might say in the half-plane case, there's another map between them, namely this non-surjective inclusion map. And relative to this other map, they're now not equivalent. Now, I take this to be making basically essentially the same point that I am, that to distinguish isomorphic models, one needs to make use of something that's past the isomorphism. But I think that perhaps thinking in terms of the structure one needs to fix and how it needs to be interpreted in the way that I have is helpful in understanding physically what allows one to distinguish these cases. Talking in terms of the different maps between these models might seem like a more abstract way of saying this, but I don't think there necessarily needs to be a preference. So just to draw some implications of what I've said here, what I've said is that isomorphic models that are descriptionally different can be used to represent distinct situations within a theory, even though they can also represent the same situation equally well. And they can be used in this way when one can fix the interpretation of some additional structure which enables one to distinguish the models physically. And if one removes the so-called redundancy that comes from having multiple isomorphic models of a single situation by reducing them to one single identical model, then one loses the ability to represent these situations as distinct, since this prevents one from being able to even descriptionally distinguish these models. And so one can't use any additional structure to physically distinguish them. And so I think this motivates a distinction that one can draw between two kinds of physical significance that one might attach to some structure. One kind of physical significance that some structure might have is that we think that it should be part of the structure of the theory, such that models in which the structure differs are non-isomorphic. But another way in which one might say it has physical significance is not that it's part of the structure of the theory, but it still plays an important representational role in that it provides a way to distinguish physical situations that are modeled by isomorphic models of the theory. And structure can be redundant in the sense of not having physical significance of the first kind without being redundant in the sense of not having physical significance of the second kind. And so one may want to remove structure from the structure of the theory without removing the ability to talk about it at all by identifying isomorphic models where it differs. And so I think this demonstrates that the problem with the argument that isomorphic models indicate redundancy and therefore should be identified is that it conflates these two notions of physical significance by assuming that because some structure doesn't have physical significance of the first kind, it also doesn't have physical significance of the second kind, and so one doesn't need any way of talking about it. Okay, so now I'm just going to turn back to Rovelli's argument and demonstrate why I think this argument might be seen to have a very similar form to the one that I just presented. So one thing that's important is that when one determines what the gauge variables and the observables of a constrained Hamiltonian theory are, one hasn't yet specified which one takes to be part of the structure of the theory, in the sense that which of the variables are such that if they take a different value at a point in phase space, then this gives rise to a non-isomorphic model of the theory. And so if one takes models related by changes in the gauge variables to be isomorphic, then the constrained Hamiltonian argument seems to be analogous to that argument that what distinguishes isomorphic models is excess that should be removed. And so I think this provides one way to interpret Rovelli's argument, namely that the problem with the constrained Hamiltonian argument is that it conflates these two senses of physical significance. And just to highlight why this is the case, let's go back to those last two steps of that constrained Hamiltonian argument. They said, since the different evolutions are physically equivalent, the gauge variables are not physically significant and therefore are redundant to the theory. And since they are redundant, they should be removed from the theory in order to remove the underdetermination present. So now in this way of understanding Rovelli, what we can see him as saying is that partial observables are not physically significant in the sense of being part of the structure of the theory, and so are redundant in the sense that we shouldn't take them to correspond to non-isomorphic models of the theory. But this doesn't lead to the conclusion that they should be removed by moving to a reduced phase space where they can't even be described, because they are physically significant of this second kind, because they have a kind of representational role. So while I think this is one way to interpret Rovelli, well, understanding that he thinks these aren't physically significant of the first kind is precisely because he doesn't think that they are predictable in the theory. And precisely because then they're not predictable, this is the sense in which any choice of one value assigned to that gauge variable or another is equally good as each other. And so we think that they ought to be isomorphic in the theory, any of these choices. And on the other hand, I think we should take him to say that they're physically significant of the second kind because they do play an important representational role for him. They play this role in the coupling of variables. So briefly, I'm just going to turn back to this example that we used for Rovelli's case, this spaceship example, and just to see how it seems to exhibit just the same kind of representational role that I discussed in the context of isomorphic models. Now, in this case, it seems that if one removes the gauge variables by formulating the individual Lagrangians in terms of the observables by getting rid of the gauge variables, then one loses the ability to talk about spatially shifting each spaceship system. This just gives rise to an identical state of affairs. And so it seems that considering the coupled system is just like fixing some additional structure in order to physically distinguish shifting one of the systems. And so I think this spaceship example can be seen as exactly analogous to the half plane and the swerving example, in that they both seem to show that one shouldn't get rid of having these isomorphic models because it loses the ability to fix some structure to distinguish them. And so finally, I'm just going to look at why I think this answers the questions that we highlighted for Rovelli earlier. So the first one was, what does the spaceship example play? What role does it play in showing that the gauge variables in general should not be removed from a theory? Now we see that it's not just about the difference between a subsystem and a combined system, but it's more about the representational role that gauge variables might play in distinguishing physical possibilities that one takes to be important in the theory. And second, what is the physical significance of partial observables supposed to be in contrast to the complete observables? Well, now we see that the complete observables, unlike the partial observables, are physically significant in the sense that we want them to be part of the structure of the theory. But the partial observables do have a physical significance in the sense of playing an important representational role, despite their value not being fixed by the theory. And so I think this demonstrates how Rovelli can take it to be the case that partial observables are not predictable and yet still have some physical interpretation within the theory. Cool. Okay, so I'm just going to end with some questions, some open questions that I think one might still have for the arguments that I've given here. So the first question is, how do we distinguish which structure plays this important representational role from structure which we think plays no role at all? Now, I've given some kind of toy examples to demonstrate that there's some such structures which might play this role, but I don't want to say that any structure that one can define will have this kind of role. So it seems that in the cases I considered, we had some further physical grounds for thinking that there's some structure that's significant in this sense. For example, we think that there could be clocks or ways of specifying which direction one's traveling in. But I think it's an interesting question whether we could give a more general account of what kinds of structure play this role. And relatedly, in the constrained Hamiltonian formalism, there's an important class of cases where the Hamiltonian itself is a constraint. And this leads to this so-called problem of time, that for theories that are reparameterization invariant, if we run through the constrained Hamiltonian formalism, we seem to get that nothing changes over time. And I think it's an interesting question whether these cases differ in terms of the role played by the gauge variables. Okay, cool, thank you, that's all that I have.
And thanks so much, Clara, for that. That was really great and really, really interesting. I'm sure everyone's got loads of questions to ask you. What we normally do is have a 5-minute break. So maybe at 28 minutes past 5, we'll regroup and go to question and answer section.
Cool, perfect.
Cool, so I'll see you all at 28 past. If you want to, so we'll start with students and then go on to staff. If students want to in advance just put like Q for question and F for finger, if you want to do that in advance, that's great also. But yeah, I'll see you all at 28 past.
Cool. David, should I stop sharing my screen, do you think? Would it be better or should I keep it up?
What do you think, Kareem? I'm not really sure. I guess maybe go to the...
I think stop sharing. There's not that many. It was mainly text anyway, so I think it should be more fun to do it without the screen.
Cool.
There you go.